Okay, full screen here. I'm looking at lesson 12. A little bit different type of lesson set so that we can see some patterns. Kind of follows the solving equations videos, but I also have some graphs and a few challenging moments as we move along, I think. Some new things to see. And also when we're solving these equations, we also want to get a graphical approximation to get a feel for, we're working with calculations. Do we know what we're looking at? Pictures are very helpful. Got the marker, the eraser, and Rennie the cart ready to go. That could be a first, definitely. All right, so let's look at it from a graphical standpoint first. I've got the equation of a line. And it's going up at a 2-to-1 clip. That looks to me to be 2-to-1. 2-to-1. All right, and I'm going up to a height of 18. Now, 18 could have been written as 0 times x plus 18. Linear functions are either increasing, not increasing, or decreasing, So this is a line. 0 for a slope. It's got to exist. So if this was a function, if this was f of x equals 18, then f of 2 equals 18. F of 3 equals 18. F of anything equals 18, and that's your graph. So we're looking for a solution to one aspect of a coordinate. This has an x and a y, and we are simply solving for the x. What x value makes that work? Now, I encourage you to figure it out from the slope context, considering we're starting at an x value of 3. All right, so how many of these would you have to draw to get to 18? Pause the video and think about it. Well, I know I'm at a height of 4, right? I'm at a height of 4 and I got to get to 18. I got to go up twice, 7 times. But that's the vertical, up 7 times vertically. There's also a horizontal commitment. Forget I said that. There's also a horizontal context, which means that if I'm going up 7 times vertically, I've got to go over 7 times. I didn't draw that very well, but I got to go over 7 times horizontally. So from the context of that's I guess what I'm hoping to say. It looks like I got to add 7 to 3. So let's see if all those numbers show up in a simple solution. First, I subtract 4, 14. Well, that's what I said. From 4 to 18, you got to travel 14 units. Okay, but I'm going up at a clip of 2-to-1. So vertically, I just need the number 7, because if I double it, that gets me the 14. And if I'm measuring from 3, then I got to be 7 units to the right of 3. And it sure looks like our x is 10. That's what I hope you got when you thought about doing it non-algebraically. All right, so that's the first problem. The second one is following the same line of reasoning, except we have one more calculation to consider, which means that if you're looking for patterns, we have one more inverse operation. But I've got 3, I've got 4, but in this case, I have a parabola, and I'm trying to hit a height of 18. Well, before I hit a height of 18, it'd be nice if I had some measurement here, something to help me, so I'll put a 0 in. 0 minus 3, negative 3 squared, 9, 18 plus 4, ooh, 22. 0 gets me 22, which means that 6 has to get me 22. That's enough to say 18 is below it. So I should have numbers between 0 and 6. That's a smaller line segment than that. So this x is a little bit to the right of 0, and this x is a little to the left of 6. Let's get some more room here. Maybe if I do this more often, I'd remember to do that on this side. So let's solve it, see what those numbers are. Still 14, still 7, but now that extra inverse operation. Well, I know that's a little less than 3, right? And so if the last step, 3 plus or minus the square root of 7, has to be a little less than 3 plus 3. And a little less than or greater than 3 minus 3. Right? Yeah. Okay, so this is to the left of this number, 3 plus the square root of 7, is smaller than 6, and 3 minus the square root of 7 gets me the symmetry that I'm looking for. All right, absolute value. Now, I've been teaching absolute value it's usually the rule in my class, the simplest, easiest way we adopt. But I think that to enrich an understanding of this, learning to write these in piecewise functions is essential. Okay, it's an easy one to work with, and it takes time to process what a piecewise function is. But in terms of getting an answer, if I wanted to speed this up, I would simply do the positive. Okay, and set that to, I've lost my train of thought here. What am I trying to solve? I erased it. No wonder, 18. Okay, setting it to 18. Okay, well, we've kind of got that already. We know it's 10. So if I'm 7 units from 3 to the right, then I got to be 7 units to the left. So -4 and 10 are the numbers that I am looking for, I believe, unless it's too early and I'm not awake. So let's go do it. And we'll do it. If I wasn't teaching piecewise, I'd probably take the shortcut, which I think works in most situations, but I think there's a little issue with the plus minus, putting it on the right, but I'm going to put it on the right anyway. 14, 7, plus minus 7, 3. 3 plus minus 7 is what we talked about. Certainly works here. Generally speaking, the plus minus usually goes here, and then you can swing it over. I assume, maybe I'm misremembering, and not sure. But I should have done the absolute value first, same way we did the quadratic, except it's got linear components. And we want a height of 18. Well, when I put 0 in on that 10, 0 gets me 10, and therefore 6 has to get me 10. So I am looking for numbers. 4 to 10 is 6 units. I'm looking for something a little bit more than that. So it would intersect up here somewhere. All right. And what are those values? Does it look like that could be 10? Geez, I hope so. 3, 6, 10. Does it look like this could be -4? Well, let's add up -4 and 10, which is 6 divided by 2, which is 3, which is the center. So there's lots of ways to check your work. You always like to check your work from a different perspective because, trust me, you do it the same way, you're liable to just fly through something and make the same mistake. So it's nice if you can check things from different perspectives. So let's look at the domain restriction for this calculation on the left. That square root is numbers have to be bigger than 3. And there's a discussion to be had at some point, but not right now, about why. And so I need a value over there to work with. It'd be nice if I had a user-friendly square root. So I'll do this one. 2 times the square root of 25 plus 4. Okay, well, that's 14. We'll put it here. So I get 14 when I pick a number like 28. So where is 18? 18 is out here somewhere. So I got a much bigger number than 28. Let's see if we can find it. I'll line up my equal signs here. Not anticipating coming down. Maybe I'll learn to do that if I keep doing this. So what are we going to do? We're going to divide. Oh, we're going to subtract 4. We're going to divide by 2. Seems to be a pattern here. And I'm going to undo the major operation of square rooting by squaring. And then I'm going to add 3. That's believable. I think it's believable that out here somewhere, I mean, I could have done a better job of 10 units. From here to here is 10 units. That's not too bad. I think it's a little further out, but 52 looks like it's quite believable. So let's move on. Let's do a perfect cube. This is a perfect cube right here. Has no linear component to it. So it looks like this. And I think by this stage, you're probably going to guess that the point of inflection is 3, 4. Why don't I square and get the squared term here real quick? Minus 3x times minus 3x is minus. Do I want to do this? No, I'll leave that for later when we're putting cubics in graphic form. All right, I'm not going to expand it. All right, so what do we have here? We have a cubic. We're looking for a height of 18. Let's put 0 in again. So 0 gets me minus 27, minus 54, minus 50. Oh, 0's over here. Oh, yeah, it should be. It's got to be to the left of 3, and it's minus 54. So that's 54 units of change. So I'm looking for 18 units, 14 units above 4. I'm guessing my x is right about there. Now, to get to -5, I had to go back 3 units. So my value should be something between 3 and 6. I should get answers between 3 and 6. Say I'm on a final exam and I got plenty of time to check. So what do I have? Well, looks like we got the 14 again. Looks like we got the 7, but what undoes cubing? Cube rooting. I know that is less than the cube root of 8, right? So this number is, let's just say it's less than 2, and then I'm going to add 3. So let's add a number that's a little less than 2. How about 1.98? Well, we said I didn't want to move 3 units from 3. I'm only moving this many. Seems believable to me. But your exact answer is 3 plus the cube root of 7. You can always see your answers work. Let's put 3 plus the cube root of 7 in here. 3 plus the cube root. No, I did not say plus minus. This function only has 1 point of intersection. Odd roots do not have plus minus. So the 3's cancel. Square root of 7 cubed. Ah, I misplaced that. That's why we checked it. Right? I need to write the cube root. I did over here, but I forgot to write it on the answer key. I caught it. So now the cube root of 7 cubed is 7 times 2, 14 plus 4, 18. All right. So that one's done. Am I even? Yeah, I think I'm good. All right. So exponential growth, bigger than 1, right? If I do something and multiply it 6 times, I can't even reach up there 6 times. And this would be 1/6. I hope you get a feeling for that trajectory. But this thing is 4 units above what I just drew. So let's say y equals 4. Let's see if I can put that over here. Y equals 4, I'll get it away from the equation a little bit. So what are the easiest 6 to the x's that I can do? I think 6 to the 1, 6 to the 2, but I am a very big fan of 6 to the 0 because that makes the number 1, and then we have some multiplication. So what makes this thing 0? 3. So to me, it's highlighting that, and we're changing by 1, by the way. So I'm going to use 3 and 4. So 3 gets me my first jump of 2. And then 4 is going to get me 6 times that jump. And 6 times 2 is 12, plus 4 is 16. And my first jump is 2 plus 4 gets me 6. So there's my graph, a quick facsimile. And I want 18, so I should get an answer just a little bit bigger than 4. That x is to a little to the right. So let's find it. Subtract 4, divide by 2. And now you need to know the inverse of this. And we've been putting it, I've been putting it on every lesson set. Doesn't mean you've seen it, because a lot of times you're still working too sequentially. You're better off just looking at the video 2 or 3 days in a row and then trying every problem. You'll go through it much more quickly. All right, just a suggestion. So the inverse of 6 to the x is log base 6 of x, and we're going to keep saying that till May 15th. So at this stage, I've got to get, I'm looking for an exponent on top of 6. That gets me 7. I'm looking for an exponent on top of 6 that gets me 7. Right? And what is that exponent? Right now, it's x minus 3. So therefore, x is equal to 3 plus log base 6 of 7. Now, you got to go to a calculator if you want a lot of decimal accuracy. I don't know what 7 is in E notation. I probably shouldn't have said that right now, but I do know that one. So I can't do this without a calculator. I don't know how to do it without the calculator, but I could get an approximation here from the mind's eye. It's a little bigger than 1. 6 to the 1 is 6, so it's got to be, this exponent's got to be a little bit bigger than 1. So my answer has to be a little bit bigger than 3 plus 1. Yes, it's a little bit bigger than 4. Now we got e to the x. Well, I picked this for a good reason, I hope. Except I forgot to change the worksheet, so no, doesn't have a good reason. Anyway, E is 2.71, so I've got another one of these. And at least I can see I'm jumping by 2 the first time if I pick the right number. And then this is divided by 1, so it would be nice, maybe I did pick the right number, if I make that 3 times bigger. 6, well, that's not 12. I should have hopefully done a little better job here of giving you a different question, but this is what's going on, right? Because I'm a big fan of e to the 1.1. It's on your memorization sheet, handed out day 1 of this class. So e to the 1.1 is approximately 3. And I told you I'm a big fan of e to the 0. Anything that's 0 is 1, which is why I'm going to get a jump of 2 here. So what makes this e to the 0, which makes it 1, 3. 2 plus, oh, forgot to write y equals 4. I hope you didn't. 2 plus 4 gets me that. So there's a lot of similarity there. The only difference is I want to triple each and every time with this function because I can standardize and then graph more quickly. So what makes this 1.1? I hope you can see 4.1. 4.1 gets me 3. So 4 plus 6 gets me 10. And I want a height of 16. 16's bigger. It's up here. Bigger than 10. So I got a number that's going to be bigger than 4.1. Let's find it. Subtract 4. Divide by 2. What's the inverse of log base 6? 6 to the. Wow, are we going up fast? Woo! We are on that section of the curve. Wow. Wait a minute. Something is wrong with my analysis. Oh, I'm looking at this, but I was solving this. Oh, there you go. That was a real good one. Go ahead, Yasser. Chime in on that one. Talking so much. Yeah, I'm getting old. We're solving this equation. Holy cow. Glad I checked it graphically. Didn't walk away from a test feeling foolish. 12 divided by 2, 6. So now I want e to the x minus 3 equals 6. What's the inverse? Well, the inverse of exponentiation is logging. Okay, and I'm hoping you're pausing the video. I pretty should have said that to begin with. And you're thinking, well, pause right now. And I hope you say x minus 3 equals the ln of 6. Wow. So what's my answer? 3 plus the ln of 6. And I'd like you to tell me what that is, because those are test questions. I'd like you to approximate that for me without a calculator. All right, then we're going to get a feel for that x value, which is, oh, I erased the graph. Anyway. So I'm looking for the exponent base E notation. I have to write 6 in base E notation. Well, I know 6 is 2 times 3, and I know 6 is equal to E approximate. Remember, I said approximate. E to the 0.7, you're supposed to be memorizing that. And we've already said this one enough. E to the 1.1. So 6 to the what equals this? Well, 6 is equal to E to the 1.8, right? Approximate. And I'm looking for the exponent on top of E that gets me 6. I guess I just found an approximation of 1.8. So my answer should be 4.8-ish. My exact answer is this. Doesn't hurt to put that in here right now. Let's do E to the 3 plus ln of 6 minus 3. Let's see what we get. See if we get 6. Well, I see the 3's canceling. And this is saying, I now have the exponent I put on top of E to get 6. Well, guess where that exponent is? It's on top of E. I'll say it again. This calculation is looking for exponential activity on top of E that gets 6. I think we have established that it's approximately 1.8. E to the 1.8. So this means E to the what equals E to the 1.8. I would hope you'd say 1.8. And maybe you can make the connection that these operations are what? Inverses. Okay, so we're talking about problems we've been doing now for a week or two, but we're getting into more in-depth looks. Nothing wrong with that. So now I've got the inverse. Well, I should have had this one thing. Here we go. So you're looking at exponential growth, I believe. No, that's decay. You're looking at exponential growth from this perspective. If I switch the x's and the y's, that's the kind of graph I get. Now, I learned something from a previous video. There is no multiplier here. There is no multiplier. So I've got a graph that's going to have 1 and E as differentials. But I'm not going to use E as a differential. I'm going to use 3. That's how I'm going to graph this from that perspective. So let's see it materialize. Well, the first thing I see is x equals 3 is the most important part of that graph. If you don't pick numbers bigger than 3, you go ahead and put this in your calculator. See what it says. Go to decimals. Go to Google. Type ln of 0. It's undefined. Whereas any other number is defined as long as it's positive. You can't do the inverse of growth and decay unless you have something to start with, right? Time to amount. If you don't have any amounts, let's not have the discussion about growth and decay. So amounts have to be positive, and this is all about amounts. It's got to be positive. So numbers have to be bigger than 3. I'm going to pick 4. So 4 minus 3 is the ln of 1. Okay, what do you put on top of E to get 1? I hope you say 0. That disappears, you get 4. So right now, what did I pick? I picked the 4 and got a 4. Now keep your eyes open. Whenever you make the parentheses 0, see how many times you get the constant. Keep an eye open for that. All right, what's the next number? Well, I'm dividing by 1. So why don't I put a 4 in here? Oh, sorry. I'm on this part right now. I like the number 3 because I know what the ln of 3 is. Pause the video. Think about it. I hope you say it's approximately 1.1. So I'm going to pick the number 6 because that makes this 3. And notice how far 6 is from 3. 3 units. So there are differentials here that can help guide us. What would the next differential be? It would be 9 if I drew it well. What would the previous one be? It would be a third. And what about these? How about 1/9? And if I pick those numbers, I should have the same gap. Should have done a better job of drawing. All right, it would be the same, what do we want to call it? Vertical change. If I'm using those user-friendly numbers. Okay, so let's look at, why did I do that? Okay, so there's our graph, 4, 4. And 6, did I get that answer yet? 1.1, 2.24, 6 point, what did I just say? 6.2, I think. Okay, so 2.2 units of change every time I do this. So that would have been 2.2 units of change, whatever that is. Here, right, is going to get us the next one, which I'm not sure we don't need right now, but we're looking for 6. Well, that's easy. 6 is here. I need a number to the left of 6. Let's solve for it then. Subtract 4. 2 divided by 2. 1. What gets me ln of what gets me 1? X minus 3 equals e to the 1, which is approximately 2.71. Exact answer, 3 plus e. Approximate answer, 3 plus 2.71. Is it believable that this x value is 5.71? If that one is 6. This is what you're trying to see. Now, the next problem is pretty early in our semester to be asking you to solve, but it's a sinusoid. I'm not looking for a general solution. I didn't even ask for one. I didn't even tell you what I wanted for a solution. I want one revolution, just one revolution, and this is one revolution from the sine curve, 0 to 2 pi, right? The circle maxes at 90 degrees. So as I start here and I go up to 90, I come back down to where I started from. I go to my minimum of -1 and then back again. That is the period that we're going to try to replicate. So how do you graph this? You put some dotted lines down. This is the middle, and I'm going up and down 2. I'm going up to 6, and I'm going down to 2. And we're trying to find when this is 6. And I can do one period of the sine function, like so. Question is, this one started at 0. Oh, I guess that has to be 3. And then I guess it has to end at I to 4 at 3 plus 2 pi, once around the circle, which is what we did a second ago. And I'm at a max. I can see I'm at a max. I just told you pi over 2 gets you a max. So I think 3 plus pi over 2 is this location. Again, I'm just planting seeds here. We haven't even done the unit circle yet. But I have asked you to look at the video, what's a radian? All right, so you got to start there in order to understand this stuff. All right, so 3 plus pi over 2, let's put it in. 3 plus pi over 2. 3's cancel. Sine of pi over 2 is 1. 2 times 1 is 2, plus 4 is 6. Okay, and a conversation is starting here, which we will develop over the next several weeks. All right, so I got a box. Did this in another video. And I think if I got a box and I got an equal sign, then I got to have a box over here. This is a very non-traditional way of looking at this, but I like to play. And on this side, I got 2 dimensions. And on this side, I got 3. So you pause the video and see if you can figure out what that answer is. Well, if we take out what's common, the x squared's gone. Well, if I get rid of the x squared, where's that missing dimension? I think it's times 1. I think so. Because if you square things, you only get positives, right? And I don't make it -1 because -1 times -1 times -1 is a negative, but it's an interesting way to look at it. So I really had a volume situation on the left, and I actually have a volume situation on the right, which really makes me wonder about like terms. But I'm not going to go there right now. All right, I might develop that thought and see if it leads somewhere, and I think it might. But I'll start with a quadratic. So, okay, what did somebody figure out at some point? 7 equals 7. There's something that's true. And 7 minus 7 equals 0. All right, so why don't we subtract, get our like terms together, get our variables together. Let's keep the division going to be positive. So that has to be true. And so what do we do? What did I do before? I took x squared and I kind of took it out of the equation in order to find that missing dimension. But I'll write this as a product, x minus 1. And there's a couple of things that stare me in the face. X squared could equal 0. All right, so let's let x equal plus minus the square root of 0, which I think is 0. So what happens if I put a 0 in? If I put a 0 in here, I get nothing. If I put a 0 in over here, I get nothing. I guess nothing equals nothing. I guess 0 is one of my solutions. So when is that 0? When it's 0. When is this going to be 0? So I get nothing equals nothing. When x is 1. So what does x cubed look like? Flat at the origin, because there's no surface area on the cube. And that's how the volume of a cube changes based on its surface area on 3 sides. X squared looks like this. It's hard to do. God, it's hard to come up like that, right? But that's where they're intersecting 0 and 1. Continuing on. X squared plus 6x equals 11. Wow. I can't factor that. I can't draw it. I mean, I can draw this. That's a rectangle. X times x plus 6 equals 11. Jeez, this is tough. This is a tough one. Yeah. So what do? Well, we got to use inverse operations. And what's the inverse of squaring? Square rooting. And this isn't a square. So let's turn it into one. Let's turn it into x plus 3 times x plus 3, which is x squared plus 6x plus 9. This is x squared plus 6x. Why don't we get rid of this 9 and then set it to this side? Okay, now I'm sure maybe given what I did a few minutes ago, maybe I can play around with this with 1 times 11 over, I don't know. But right now, I've got a nice square, okay, which is x plus 3 squared minus 9. That's another name for x squared plus 6x, and I'll set it to 11. Well, now it's a piece of cake. Add 9, 20. Take the inverse of squaring, plus minus square rooting, and then subtract 3. And since we're learning how to deal with that, why don't we write it as 2 root 5? Okay, so that's a number a little bit, 2 times 2 is 4, so this number is a little bit bigger than 4. And minus 3 minus something a little bit bigger than 4 should give me an answer of, something around negative 1.5, I guess. And then I should get an answer of minus 3 minus something bigger than 4. I got to be to the left of 7. So I got to be to the left of this number, and I forget. I said something around that, I think. Anyway, getting tired. I'll start making more mistakes. So let's look at it graphically. From the original, I can see 0 and negative 6. I can see negative 6 gets me 0, and 0 gets me 0. That's true for x squared plus 6x. Where's the height of 11? Height of 11 is way above it, so I misspoke. One of my answers had to be bigger than 0, so I made a sign error there a minute ago. But my other answer was correct. To the left of negative 6, negative 7. So I am going to be okay to move forward with 3 plus or minus 2 root 5. At this stage of the video, I'm certainly not starting over again. So let's look at this problem. Well, I'm going to stop drawing the answers here for this one. I'm just going to do it because it's starting to take a lot of time. So I'm going to add 5 to this side, and then I can see that this is factorable. So I have answers of negative 5 and negative 1. I don't like dividing by negatives, so I'll make that 0, move this to the other side, plus 5x. Based on what we did before, I'll take out what's common, x times 7, x plus 5. My two answers are 0 and negative 5/7. All right, now we're going to turn, nope, not yet. All right, so just flying through these, I'll move the 3 to the other side. All right, I can see it's factorable, but if you can't, b squared minus 4ac can help. If that's nice, it's factorable. B squared, 25, minus 4 times a, 2 times c, negative 3. That's 49, very nice. So it's factorable. So 2x and a 3 out here, that gets me to 6. 1 more x gets me to 5. I want it to be positive. So the answers were 1/2 and negative 3. Okay, 4x squared equals 10x equals 6. Move the 6 to the other side. And I hope you can see when you divide by 2, you got the same answer as above. All right, some fresh problems now. I got tired of doing the same thing there. All right, should never get tired doing math unless you do 10,000 problems a day. And actually, I don't get tired of that either because you trip over insights. All right. Name that tune. You're pausing the video, I hope. All right, well, I got a feeling it's got something to do with x minus 4 squared plus 7. Yep. And I'm looking at squared change from 4 to 9. I'm looking at squared change from 4 to 9. 9 minus 4, 5 squared is 25. 25 plus 7 doesn't get me to 30, but it's pretty darn close. What takes me from 7 to 30? 23. So my multiplier is a little less than 1 to make that happen. There are numbers between counting numbers, and they're not nice. They just have a place on the number line like any other place, and we want to treat them nicely. So I shouldn't say square root of 49 is a nice number. I wonder how the square root of 48 feels, or even the square root of 47. because at least the square root of 48 has a 4 in it. Of course, square root of 47 doesn't have any of that at all. Okay, got carried away. So if I had a piece of paper here and I flipped it, guess what the inverse of that would look like? It would look like that. And this is the positive square root, and this is the negative square root if we were in terms of x. But as a function, we basically look at the principal square root. Said a mouthful there, don't worry about it. So this is actually, x values are a function of y. So let's look at the first y value. I guess I can do it up here. Let's look at the first y value, it's 7. Well, just like I used to do with the x's, I'm going to get rid of that and bring in the x value of 4. Because my x values now are a function of y. What do I get if I put a 30 in here? Oh my God, I get 23 squared. I was going to say not, I'm not going to say not nice. How about not friendly? Okay, how do I get from 7 to 30? I think I got to go up. Oh boy, I just went dyslexic. How do I get from an x value of 4 to 9? 5. Yeah, some dyslexia there with me. Let's hope I didn't make a mistake. So what's this one now? Name this tune. I give you a, I think there was one more that I didn't do. I think it was, well, you look at this, see if you can sort it out. Be helpful if I help you with a visualization here. So pause the video, look at it, I'll keep going. Well, differentials is getting to be a big part of my language these days. I'm going up 5. I'm going up 5. I'm going up 5. From here to here, I'm going up 5. From here to here, I'm going up another 5. From here to here. Yeah, so if I start at 2, I'm going down 5, down 5, down 5. Did I do the table I wanted? Well, this is the one I have, so I got to work with it. So 9, 2. I'm hoping you're seeing x minus 9 plus 2 gets me in a position to start talking about change. Now, how did I get from 2 to negative 3? I go down 5. And what's the absolute value change from 9 to 6? It's 3. So let's put 18 in and see if it works. 18 minus 9 is 9. The absolute value of 9 is 9 times minus 5/3 is minus 15. Minus 15 plus 2 minus 13. I'm moving on. Okay. Woo! I got my water over there. I need it. Gunga din when I need them. All right. 4, 7 to 930. I hope we just talked about the upper branch of y squared. X equals y squared is the square root of x. So I'm going to write y equals square root of x minus 4 plus 7. What's the change going to be? Well, it's going to be square rooted change from 4 to 9. That's the square root of 5. And how do I get from 7 to 30? 23. Now, the next one's a nice little challenge. Just going to finish the video here. And if you want to take time to figure out how to write that, I don't want any negatives inside the square root, and I don't want any i's showing up. All right, so with those restraints, what's that equation? Now, I'm going to do it, all right? But I really, if it'd be more helpful if you really thought about this for a while. All right, I used to give it as a challenge question, and I wouldn't answer it for days. And once in a while, somebody would come up, maybe one student, day one would come up the next day and go, I think I got it. And I go, you do? It's shh, shh. Okay, so I don't know, maybe I should do that here. Yeah, somebody else posts the answer, and if somebody does it, I'll post it in the next video. I'm not going to give it to you. Right, you try to figure it out. All right, here's one of our perfect cubes, right? Flat at the point of inflection, because I'm going to put this one in graphing form for you very quickly. We'll see why this is flat. All right, so I'm starting at 7. I'm doing x minus 4 cubed. And I've got to get to 930. So I need some space here to change that. So if I put 9 in, I get 125 units of change. I don't want that. I want to get from 7 to 30, 27. All right. So now I'm going to show you the graphing form. And this was in graphing form. It has no linear component. There's no linear component there. This will have a linear component. Let's hope I'm at the end of the video when my brain gets tired. I don't want to make a big mistake. Even if I do, I'll correct it in the next video. So minus b over 3a. That's where the x value is for the point of inflection. 12 divided by 6 is 2. So therefore, I now know I have 2 times x minus 2q, x minus 2 for part of the graphing form. Now I need the value that goes with 2. So I plug it in. 16, I believe, is what I get here. That has to be minus 48 because there's a 3-to-1 component. And when I add these together, I get twice that term. So I can jump to that quickly mentally. Now, if I put 2 in here, I'm subtracting 20 and I'm adding 3. Okay, I think I'm okay. Minus 52 plus 3 minus 49. All right, let's drop in c minus 3ah squared so we can see what is happening at the point of inflection. At what rate are we changing? C is minus 10 minus 3 times a bunch of 2's. So 8 minus 24 minus 34. I am now ready to graph this. Okay, where can I graph it? I'll graph it over here quickly. Yeah, you can see. I now know, because I'm going down at the point of inflection, that I have a graph that looks like that. I'm at 2 comma negative 49. This 2 is that value right there. And that's where I'm going down the fastest at minus 34 to 1. Okay. Now I know my y-intercept is 0, 3. So my y-intercept is up here. I don't know which side up here I'm at a height of 3, but I'm definitely at a height of 3. And looking here, I'm decreasing at 10 to 1. I now know I'm here, going down at 10 to 1. So 0 gets me 3, and I'm going down at 10 to 1. Well, at some place, I level off. And that can be found by h plus, or in this case, minus the square root of 49, because that's how I get up to that location, divided by this 2. All right, what was h? H was this 2. I don't usually like same numbers. So the square root of 49 is 7. 7, square root of 2 is 1.41. 7 divided by 1.41 is about 4. So the square root of 4 is 2. So I'm near 0. Well, that's good. I'm near 0. I butchered, I'm sure, the approximation, but I'm near 0. So I can believe that. That's that x value. And I think I can see the cubic taking over. Once I get past local behavior, this starts to dominate. Locally, that dominates. So what I had was a graph that was a perfect cube, another function that was decreasing, and when I add the two, the rate of change comes from the linear component, because the cubic is flat there for reasons we will examine later in the term. All right, let's hope I didn't make a mistake. I'll do a quick check with the number 1. If I put 1 in, I get minus 10, minus 20, plus 3, 17. If I put a 1 in, I get 17. Ooh, I don't like that. I hope it's negative 17. 1, minus 10, 2, minus 12, minus 10, minus 20. Oh, good, it was minus 17, because 1 is in between here, right? And if I put 1 in here, I should get minus 17. Let's find out if we do. Minus 1, minus 2, minus 3. Oh, no. Oh, my God, I must have butchered. So, oh, no, that's going to be negative times negative. Minus plus 34, minus 49. Well, that's minus 15, minus 2. Yep, minus 17. Ooh, I'm glad I didn't make a mistake. Running out of breath. Leaving that one as a challenge. Now we're over here. Name that tune. I'm just going to name these very quickly at this stage. I got 5 graphs to go and I'm running out of steam. So this one is 10 plus 5. Next time it's not 5. From 10 to 25 is 15. So I have a tripling function of differentials. Hopefully that looks 3 to 1. X minus 1900. And that change in elapsed time is 103 years. All right. Go to rapid fire. Go to exponentials and logs. You'll find some rapid fire graphing of exponential functions. You'll get 5 practices in a row. Okay. Now I'm going to do this one. And this one's going to mimic that one now if I pick the right numbers. So I got y equals 10. I've got a jump of 5. I'm going to make a jump of 15 with the correct number. So 1900 minus 1900, e to the 0, 1 jump of 5. 1901.1 minus 1900, 1.1, e to the 1.1, 3 times 5, 15. So there's my graph. I've got 1900, which makes the 0, gets me 15, and 1901.1, when I subtract 1900, gets me 1.1, e to the 1.1 is 3, I get a jump of 15, I go to 25 approximate. All right, I see x equals 10. Right? I think I'm going to get the inverse of the one up there, right? I think I gave you that one so that you could see the inverse. All right, so now I'm at 15. That's a jump of 5. I'm at 25 from 10. That's 15. Sorry for the same numbers here. So x equals 10. Dot, dot, dot. Boom, right? If I'm multiplying by 3, that one's going to be 5/3. That one's going to be 5/9. The next one's going to be 45 if I jump the same amount. This is going up very slowly, and I don't even know what I'm looking at. I'm not solving equations. I feel like I'm back on the other board. So let's get that x equals 10. Let's get the shape. Let's put the numbers in that we see. So I want to get 1900. I think I just did, I forget what I'm doing now. I have the graph. Oh, so I wanted the equation. All right, I want the equation. So y equals, I'll start at 1900. I got to add 25 to get to 19, to get to 2003, sorry. Oh, geez, dyslexia. Okay, time to chime in. Yasser, time to get on me. 2003, 1900 to 2003 is a jump of 103. It's a logarithm. I know x equals 10, so x minus 10. My first jump is 5. When I throw 25 in, 25 minus 10 is 15 over 5. So maybe you can, go back on the whatever I was talking about to see those differentials. They're not hard to see. They're right here. All right, horizontal differentials. And there's your base 3. And I like to mimic this with base 3 by the following. I see x equals 10. I see that I want to make a 0, I just did. Okay, now I want to make this a 1. Well, 15 gets me that. All right, and if I put 15 in, this becomes 0, I get 1900. The only thing is, I like the ln of 3. I like 1.1. So if I make this 3, 15 and 10 is 25, right? I'm mimicking, but it's the ln, right? So it's really 1.1 when I make this 3. So this really becomes 1.1. So I got to go to 26.1. And then I've got that same jump I had before, 5 and approximately 15, which gets me to a year of 191.1. Okay, kind of getting lost here at this stage. What I'm asking and when. Whew, more sleep would be appreciated on my end. All right, so last one. All right, not going to belabor the point here. Sine function, but I'm starting at the bottom of the circle, a minimum. When we're at the top, we're at pi over 2. The circumference of a circle is 2 pi as measured from 0 once around. So that's 3 pi over 2. So I'm going to make 1900 act like 3 pi over 2. Okay, and what am I going to measure from the center? What's between 15 and 45, 30? So I have a sine function multiplying by 30, makes all those ones and negative ones go up 30 and down 30. Wait a minute. I was at 30. So I want that to be 15, excuse me. Okay, so 15. So now when I put 1900 in, and I'm also measuring from 30. So I got to put, I already wrote that here. You can tell I'm tired. 15 plus 30. Okay, I'm a little too close to it and the sun's in my eyes. Hope you can see that. When this thing gets bright, I know it starts to hide the numbers. So what I have to do here is count. 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. There we go. Divided by what? 1900 and 2000 and 303 units of change. That's that function. Now I can drop it in and maybe we can see how it works. 1900, 0 times anything 0. I'm at 3 pi over 2. What's the height at 3 pi over 2? On the unit circle, -1. Minus 15 plus 30, bingo. Now we drop in 2003. 2003 minus 1900, 103 units of change drops out of the problem. I get 7 pi. From there, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. I'm now here at a maximum of 1, 15 plus 30, 45, and I just did 3.5 revolutions. Now, the cosine. The cosine is a minimum when we're talking widths. Widths are a minimum over here at pi. So all I'm going to do is change this to pi. Change this to a cosine. And now that should work. Drop in 1900, 0. I'm at pi. Well, what's the value at pi? The width, -1, -15 plus 30. I'm there. And we can see that pi to 3 pi over 2 is a change of 90 degrees. And that's how they differ. The sine and cosine are the same function, just 90 degrees apart. Okay, sorry I ran out of gas at the end there and started having trouble seeing what I was seeing. But there's practice there, and I hope you can sort it out. All right, class starts momentarily. Have a good day.